Ion exchange chromatography, theory and principle. Ion exchange chromatography is a separation technique based on the electrostatic interaction of charged surfaces. Types of ion exchange chromatography. Based on the ion exchange chromatography can be classified into two types: cation exchange chromatography and anion exchange chromatography. The principle of ion exchange chromatography separation is the reversible interaction of charged species with the ion exchange matrix. Mechanism of protein separation in ion exchange chromatography. These are the two mechanisms mainly used in the separation of proteins in ion exchange chromatography. One is pH-based, and the other is salt-based. pH-based mechanism. Separation of molecules by ion exchange chromatography relies on differences between the net surface charges on the solute molecules. Proteins, for example, contain numerous groups which can ionize to varying extents depending on the pH of the solution. The ionic state of these groups is highly dependent on the pH, and as a result, the net surface charge of a protein will undergo a change as the pH of their environment varies. At the isoelectric point of the protein will have little or no tendency to bind either to a cationic stationary phase or to an anionic stationary phase. At pH value below the pi, the protein will have a net positive charge, and will tend to bind reversibly to the surface of a cation exchange resin, that is, one that has negatively charged groups at that pH. Note that a cation exchange resin is anionic, having negatively charged groups, while an anion exchange resin is cationic, since it has positively charged groups. Binding to the matrix requires that buffer ions that are bound to the matrix during the equilibration process be displaced by the solutes of interest. Thus, exchange of ions takes place at the surface of the matrix. On applying the sample, conditions are chosen so that as many as possible of the unwanted solutes do not bind to the resin, leaving the molecules of interest bound to the matrix. Salt-based mechanism. To optimize binding of all charged molecules, the mobile phase is generally a low to medium conductivity solution. The adsorption of the molecules to the solid support is driven by the ionic interaction between the oppositely charged ionic groups in the sample molecule and in the functional ligand on the support. The strength of the interaction is determined by the number and location of the charges on the molecule and on the functional group. By increasing the salt concentration, generally by using a linear salt gradient, the molecules with the weakest ionic interactions start to elute from the column first. Molecules that have a stronger ionic interaction require a higher salt concentration and elute later in the gradient. The binding capacities of ion exchange resins are generally quite high. This is of major importance in process scale chromatography, but is not critical for analytical scale separations. Types of ion exchangers. Based on the charge retention with respect to pH, ion exchangers can be classified into two types, strong and weak. Strong ion exchangers do not show any marked change in their ionic states with changes in pH. They remain fully charged over a broad range of pH values. Whereas weak ion exchangers does not retain their charge over wide range of pH. Advantages of strong ion exchangers. The development and optimization of separations is fast and easy since the charge characteristics of the medium do not change with pH. The mechanism of interaction is simple since there are no intermediate forms of charge interaction. Binding capacity is maintained at high or low pH since there is no loss of charge from the ion exchanger. Most proteins can be separated on either strong or weak ion exchangers. If strong ion exchangers do not give the required results, try a weak exchanger. These offer a different selectivity to strong exchangers, but their exchange capacity changes with pH. Factors affecting ion exchange chromatography. The following factors have effect on the separation efficiency and resolution. pH of the mobile phase, ionic strength, mobile phase modifiers, temperature. Buffers used in ion exchange chromatography. Cationic buffers are used for anion exchange chromatography. Example, alkylamines, tris, aminoethyl alcohol. Anionic buffers used for cation exchange chromatography. Example, phosphate, acetate, citrate. Mobile phase modifiers. EDTA used for chelation. Chiotropic salts urea for solubilization. PEG used for enhanced selectivity. DTT used to prevent oxidation. Stationary phase. Selectivity is based on ligand density, spacer arm, backbone of resin material. Binding capacity. Total No of charges, per unit stationary phase volume, or the mass of protein adsorbed per unit volume. Pore size of ion exchange resin can range from 10 to 1500 Armstrong. Dynamic binding capacity, can be found out by doing breakthrough curve. Ion exchange chromatography workflow. Ion exchange chromatography is performed in the following steps: equilibration, binding, washing, elution, regeneration. If the elution process is carried out using the same buffer that was used in applying the sample, the elution is said to be isocratic. Alternately, the elution may be carried out for a while with that buffer, and then with another buffer. This is called stepwise elution. For the best results, the composition of the eluting buffer is changed as the elution progresses. The change is usually a change in ionic strength, from a less dilute to a more concentrated buffer, or, less frequently, a change in pH. This elution process is called gradient elution, and this generally gives a much better separation of solute.